Okay, so it's height above the ground. Nope. Actually, we're going to give the ground in feet. Okay, so we're going to measure the height in feet after t number of seconds is given by the position function p of t is equal to negative 16 t squared plus 64. Okay, so for problem A, we're going to find the velocity and acceleration function of the ball. Okay, and for problem B, we want to know what's the instantaneous velocity. Of the ball when it hits the ground. Okay, so let's start off with A, where we have to find the velocity and acceleration function, which is basically just a fancy way to say find the first and second derivative. Okay, so we know that the velocity function bless you, which is, I'm so used to writing F is p prime of t. Okay, so we know we have negative 16 t squared, so we can just go ahead and write our negative 16. Bring down our 2, t2 minus 1. And derivative of a constant is just 0, but we'll write out the steps anyway. Okay, so we can go ahead and multiply those two. So our p prime, let's bring that down a little bit. So p prime of t is going to equal negative 32. T to the 2 minus 1 is just t. And that becomes 0. Derivative of any constant is just 0. Okay, so we have our velocity function. Okay, now to find our acceleration function, that's just our second derivative. So we have our negative 32, and that t, the derivative of any variable is just going to disappear. So we're just going to subtract 1 there. So our second derivative is just negative 32. Which is our acceleration function. Okay. Now the acceleration is negative 32 because if you're standing on top of a hill and you just let go of a ball, gravity is the only force pulling it down, which is, I think, negative 32.2 feet per second. So when letting it go, gravity's pulling it down. It's different if you throw it. Now it's an external force outside of gravity. But if you just let it go, gravity is the only thing pulling it down. So that's the acceleration. All right. Okay, so B double prime of t is a constant. Since the only force acting on the drop ball is gravity. Okay, so we know that drop ball is not the same as a thrown ball. All right. So now we just have to find out for B, when does the ball hit the ground? Well, the ball hits the ground when the height is equal to 0. So if the height is equal to 0, that means this function has to be equal to 0. So let me kind of separate that a little bit. So the ball, we'll bring that up some. It's the ground when the height equals 0. Okay? So that means our function has to equal 0. So negative 16 t squared plus 64 equals 0. Okay? So that's when it hits the ground. Okay, so we add 16 t squared to both sides. We have 64 equals 16 t squared. Divide both sides by 16. T squared equals 4. Square root both sides, you get t is equal to plus or minus 2. We don't really need the minus 2 since time is not going to be negative, so we just use the plus 2. No negative 2. All right. So now, since we want to know the velocity when the ball hits the ground, which is 2 seconds, v of 2 is just going to equal, so remember our, not v of 2, I guess you can call it v of 2, which is just p prime of 2. Is negative 32 times 2. Okay, which is negative 64, and we're measured in feet, and our time is in seconds. Okay. So we know the velocity when it hit the ground. All right. So any questions on that? Of course, we're not taking into account wind resistance or terminal velocity or anything like that. We're just assuming there's no wind resistance or anything like that.
How did it, if it's just dropped, how did it go faster from 32 to 64?
Oh, because as it falls, normally, yeah, it kind of picks up speed. But normally, as you hit wind resistance, it kind of slows it down and all of that other stuff. But you'll be able to go into all of that in diffie-q. So if you go that far, that's when the real fun starts. All right. Any questions on that one? All right. Looks like everyone's done. All right. So let's say, for example, this time a ball is tossed. Up in the air. and its height above ground. And this time we're going to measure it in meters. Is given by the position function. Say P of t is equal to negative 4.9 t squared plus 6t plus 2. Okay, what is the acceleration at t equals 0? So pretty much as soon as it leaves this person's hand, how fast was it going? Excuse me. Okay, so we're looking for the acceleration, which means we're going to need the second derivative. Okay, so our first derivative so just finding the derivative of each term. We have negative 4.9. Bring our 2 down to the front and subtract 1 from the exponent. Plus, bring our 6 out to the front. Well, factor out our 6. And we already know that the derivative of a constant is 0, but we'll write that step anyway, just because we have nothing better to do. All right, so we go ahead and multiply these two. Okay, so negative 4.9 times 2 is negative 9.8. T plus 6, since t to the 0 power is just 1. All right, so we have our first derivative, so we just need our second derivative. Negative 9.8. Again, that's t to the 1 minus 1. Oh, we'll clean that up some. There we go. Plus, again, we know the derivative of a constant is 0, but we'll write it out anyway. 0, so that just becomes 0. So our second derivative is negative 9.8. Uh-oh, it's a little bit close. And that becomes t to the 0, so it's just 1. Okay, so at t equals 0, the second derivative of 0 is still going to be negative 9.8 meters per second squared. Okay, so it's not very likely that someone can throw a ball, was it a ball? Oh, bless you. Can toss a ball up in the air and it has a constant velocity the entire time, but that's kind of what this one is saying. That this person tossed the ball, it went negative 9.8 meters squared the entire time it was in the air, which is unlikely, but it's a story problem, so we can say what we want. All right, any questions on this one? All right. Okay, so this basically says, so the ball has a constant acceleration. Did I say velocity or acceleration? I think I said velocity, I meant acceleration. Of negative 9.8 meters per second squared the entire time, or at least until it hits the ground. Yeah. Any questions on that one? All right. I'll leave that up for a few more seconds. All right. Oh, you still writing?
No.
Oh, okay. Okay, so we know that our velocity tells us speed and direction. Okay. Now let's say if we wanted to kind of describe that on a number line. So let's say if we consider a particle moving along a number line. Okay, so our positive velocity we'll say that the particle is moving to the right. Okay, and for a negative velocity, we'll say it's moving to the left. Okay, so we'll use that to kind of draw out the, I guess you could say, the path of the particle. All right, so let's write a quick example. And I'm trying to think, can I fit this on one page? Probably not. Okay, so for example, the position of a particle moving along the coordinate axis is given by the position function say P of t is equal to t to the third minus 9t squared plus 24t plus 4. And I think it's safe to assume, but we'll just say that time is greater than or equal to 0. Okay, so let's say for problem A, we wanted to find our velocity function. Which is just another way to say p double prime, our second derivative. Okay, so for problem B, we want to know what time is the particle at rest. Okay, and for problem C, we want to know what intervals is the particle moving left to right and right to left. So we want to kind of separate that. Let's say on what time intervals is the particle moving right to left and left to right. put a little question mark there. Okay, and for D, we're actually going to sketch how that will look. So we're going to sketch the path of the particle along the coordinate axis. All right, so actually we'll probably be able to fit A and B on this page. Okay, so for A, you know our velocity function is just, oh, did I put double prime up there? I meant to put one. Don't know why I did that. It's just P prime of T. Okay, which is, we just bring our 3 down to the front, subtract 1, so it's 3t squared. Bring our 2 down to the front here, negative 9 times 2 is negative 18. Subtract 1, it's just t. The derivative of t is just going to be 1, so that's plus 24. Okay. So now we need to know what time is the particle at rest. So in other words, when the velocity is 0, it's at rest. It's not moving. Okay. So we know that when you see a particle at rest, it means velocity is 0. Okay. So we just need to know when this velocity function equals 0. So v of t equals 0, just another way of saying 3t squared minus 18t plus 24 equals 0. Okay. You can actually factor out a 3 from all of those. So you have 3 times t squared minus 6t plus 8 equals 0. And if you divide both sides by 3, it gets rid of the 3, so you don't need it. So t squared minus 6t plus 8 equals 0. Okay, so that factors out, move that right on up there, to t minus 2 times t minus 4 equals 0. So that means t is equal to t is equal to 2 or 4. So t equals 2, or I guess you can say and t equals 4. All right. So we know at those 2 time periods in time, that's when the particle actually stopped moving. All right, we'll continue this on the next page. So I'll leave it up there for a few more seconds. Let everyone finish writing. All right. Continue that here. So let's say if we know our velocity function, since we're doing C, we're just going to rewrite this part of it here as just 3 times t minus 2, t minus 1. Okay, so all we did was factor out the 3 and factor the trinomial. Okay, so we know from left to right, it means our velocity is greater than 0. And from right to left, our velocity is less than 0. Okay. So we're going to measure this. Oh, yes.
Would it be t minus 4 instead of t minus 1?
Oh, thank you. Yep, t minus 4. Where'd I get 1 from? I have no idea where I got 1 from. It's one of those random numbers that popped up there. All right, so we're going to draw out kind of a sketch number line. Okay, so we know it equals 0 at 2 and at 4. Okay, so what we're going to do is we're going to pick test values in between those boundary points. Okay, so pick and test values. Other than the, I guess it's called boundary or critical points. Points where v of t equals 0. Okay, so we don't want to pick those points because we already know it equals 0 there. We want to know where it's less than or greater than. All right, so let's say for this interval here, which we know would be negative infinity to 2, well, technically 0 to 2 since we're starting at 0, but we'll just pick one there. And might as well put 0 to 2. Okay, and this is from 2 to 4. And this is from 4 to infinity. All right, so let's say for the first one, we can actually pick t is equal to 0. Because technically it said t is greater than or equal to 0. So this could be a bracket. Okay, so if we plug in 0 here, our v of t would equal 3 times 0 minus 2 times 0 minus 4, which gives us 3 times negative 2 times negative 4. We don't have to go any further because we just need to know if it's positive or negative. We don't need to know the actual value. So we know negative and negative is positive, so we know it's positive. Okay. So we know here our v of t is greater than 0. So that lets us know that. Okay. So we have one interval down. Okay. So now we go between 2 and 4, so we might as well pick t equals 3. Okay, so that means our v of t is going to equal 3 times 3 minus 2 times 3 minus 4. Okay, which gives us 3 times 1 times negative 1. So we already know that's going to be negative. Okay, so that's going to let us know on this interval that your velocity function is less than 0.